Hello everyone, my name is John. I'm a PhD student at UCLA. Today I'm going to be talking about my final project for the machine learning for physical sciences class, which is dimensionality reduction for laminar separated flows. Fluid flows are a very important problem in physics. If we can understand and comprehend like the dynamics, the vortex dynamics, the complex interactions that occur in fluid dynamics, we can develop novel strategies for building lighter, greener, more efficient aircraft in the future. But the problem is that to study fluid flows, we need high fidelity data, which is usually obtained from numerical simulations or experiments, and both are very expensive. Experimental data, not to be willing to say anything bad about it, is very nice, but we can sometimes be corrupted with some spatial random noise that I'm trying to simulate here in this figure. In numerical simulations, to compute all these flow fields are usually extremely expensive. Our goal is to know how we can actually use unsupervised machine learning on the type of regression, actually in the form of principal component analysis, to study patterns in the flow field and possibly remove noise. If we evaluate the principal components that we obtain from this flow field, of course, you see the flow field is developed like in a vortex shading, right? We might have some ways to find small dimensions that can represent that. And we did find that with principal component analysis. We see that we can find some pairs of modes that represent the dynamics of this flow field. They kind of cluster the information that is obtained in a portion of the same amount of energy of the flow field. And if we look at these modes, they actually act as oscillators in the flow field. They have similar dynamics, they have similar frequencies that they oscillate, and they represent dominant frequencies in the flow field, and also their subharmonic. So we're actually clustering information in respect to the energy, in respect to their frequency content. If we reconstruct the flow field, you can see the effects of dimensionality reduction, where you can use only a few modes here, only 2, 6, or 10 modes, and reconstruct your almost very accurate mode, almost very accurate flow field with only a few modes. Instead of using almost all 600 snapshots, you can use 10 directions to get a very accurate reconstruction. But if we have noise, and this goes to the experiments, sometimes can have noise coming from anywhere in the measurement site, sometimes like some connections that go wrong and can pollute the data that we see here. If you have that kind of noise, this noise is actually uncorrelated. Anything that's uncorrelated will show up in the PCA modes as a very and the high order modes. So if we capture and reconstruct the flow field only using the dominant features that we have, like the most important modes that we have, we can actually remove that noise. And even if we see some things that are like sometimes polluting here, we have very large amount of noise here, we still see some things polluting the flow field, but we can see that we can denoise the flow field very well. But we know that the PCA modes, they will be corrupted by this noise, right? They capture a little bit of this noise in them, but they still capture the very important dynamics that we see. So what we see is that PCA can be used in a very nice way, supervised machine learning to reconstruct the flow field. Of course, this noise, as we say, pollutes the POD, the PCA spectrum in the end. And this PCA spectrum has a lot of noise actually incorporating the high order modes that we see. But we still have a very clear characterization of the flow field in the dominant modes. So we see in this talk, very brief talk, very fast talk, that PCA is powerful to capture important and relevant physical information from the flow field. And the eigenmodes, they can act as clusters or respective to the flow energy in a narrow range frequency. And the PCA values, they have a fast convergence, which allows for dimensionality reduction. Just to close, I'm going to say that in noisy data, we can use PCA to reduce some background noise that can occur and still be able to reveal the important physics that we see as the vortex shading, as we see in this small example. And this can be used into very large data sets, turbulent flow fields, to understand the physics that we're trying to characterize. That being said, I'm going to close my talk. Thank you very much. I'll stop sharing and finish.